Hello students, welcome back. Let us resume our discussion in section 2. In section 2, we first established the residue class rings, and then we proved this. A residue class ring ZM is a field if and only if M is prime. Now, let's consider the case when M is not a prime number. In that case, the importance comes for relatively prime. So prime or relative prime, those are important. So A bar is a unit if and only if A is relatively prime to M. How do you prove that? Well, it's going to be similar to 2.2, but I'll be more general. One direction. A bar is a unit, which means it has to have a multiplicative inverse. What do you mean by a multiplicative inverse? So A bar times something is 1, so that's going to be the starting point. So from here, somehow we have to this. So how do you do that? Suggestion. Well, let's see. What do you mean by GCD is 1? That means that can be rewritten like this. A times B plus M times, let me use some other character because it'll turn out to be B, but it's already selected here. Basically, that's what we want. GCD is 1. That means the linear combination expression is 1. Remember, for GCD, we need 3 aspects. First, a GCD is a non-negative integer, and then must be a common divisor, and then this linear combination. But then again, we don't really need common divisor because 1 divides everything there, and then it is positive, so non-negative integer part is redundant as well. So for relative prime, this ax plus my equals to 1, that's sufficient. That's necessary and sufficient. So in other words, from here, we're going to somehow get to this. That's the aim. So how do you do that? Well, A times B is equal to 1, and M times anything is actually 0. So we are in good setting, especially if we make this observation. X will turn out to be B, you see? Remember all that? No. Let's copy and paste it here. Let's copy and paste it here, and let's bring this back to the original. Okay, how do we actually work it out? Well, A times B is equal to 1 mod M, which means 1 plus some multiple of M, some Qm. And that's congruent to 0, so I can always put something in there. And flip it over, we get AB minus that's 1. And this one here, if you take GCD, this is basically 0. Excuse me, basically 0 is what we applied over here. That's 0, so yeah, adding 0. Here we have this linear combination expression. See here, down here, x turns out to be B, y turns out to be this negative q. Sorry about that. I get momentarily a little bit confused by going backward. So a times b is equal to 1 can be rewritten as a times b equal to 1 plus qm. That's how this equivalent class or equivalence relation congruence mod m can become the equality of the integers by adding 0 bar basically. And then we go ahead with this flipping over and we get the linear combination equal to 1. Make sense? Tricky, yes, but that's the forward direction. Now how about the backward direction? Similar, this time from here, we have to prove a times b is equal to 1 with all those bars. Again, we can use the same idea. What do you mean by GCD equals to 1? That can be rewritten in terms of the linear combination expression. Sum ax plus my equals to 1 like this. And then this m is going to be congruent to 0. And then this x will be my b. So that's the idea. So that's congruent to 0. So you're going to go down to a times b is equal to 1. See the idea? Okay, there you go. GCD is 1, so AB plus KM equals to 1. Okay, alright. We have the linear combination expression. And you flip this KM to the other side. So AB equals 1 minus KM. And that's 0 mod M. So we have AB is equal to 1, or AB is congruent to 1. So A bar E bar is equal to 1 bar. Again, this linear combination, that's coming into play. So we proved both directions. A bar is a unit if and only if GCD is 1. Now, if you go back to the previous theorem here, if M is prime, then it is relatively prime to everything. So every non-zero element is a unit. So we end up with a field. Now for general case, well, the number of units here corresponds to the number of elements that are relatively prime, number of integers that are relatively prime to M that are greater than 0 but less than M, or the cardinality of this set, the number of elements of this set basically, and integers between 0 and M and relatively prime to M. And this function is called Euler's torsion function or Euler's phi function. We went through this already way back in, let's see, when we studied the cyclic groups, we encountered this already, I think. And of course, in number theory, we do this a lot. So that pretty much completes the preparations for Fermat's theorem. But I don't think we'll have enough time to prove those Fermat's theorems, so let me show you. Fermat's theorem goes like this. The original Fermat's theorem goes hand in hand with 2.2. Let P be a prime number, and ZP is a field of order P. All right, that's what we already proved. And the set of all non-zero elements of ZP star. So as a matter of fact, ZP star is, it's a set of all non-zero elements. Okay, this X here excludes 0. And that's a multiplicative group of order P minus 1. Yeah, that too. ZP is field, and then, yeah, okay. Those are trivial. Now, moreover. The moreover part is something we didn't prove yet. Here we go. A to the p minus 1 power is congruent to 1 mod b. Or multiplying a to both left hand side and right hand side, we get this form. A to the p power is congruent to a. This expression here is called Fermat's theorem. And there's Fermat's great theorem and Fermat's little theorem. This one is little theorem, actually. Fermat's great theorem. Okay, I don't want to spend class time on it. Anyway, all right. That's related to 2.2. And the extension of this by Euler is related to 2.3. Now this one here is for ZP, which is a field. Now let us do this with ZM. A commutative ring with unity of order m, and set of all units, Zm star, and that has what? Phi m elements, right? Turns out a to the phi m power is congruent to 1 modulo m. So this one here is a generalization of this, because in case of prime number p, phi of p is p minus 1. So this one here is a special case of this. So this one here, 2.5, goes hand in hand with 2.3. And 2.4 here goes with 2.2. And then using those, we can do some computation problems like these. That's basically what we're up to. But then again, none of this is simple, so let me postpone all those to the next video. Next 2 or 3 videos, I guess, because we are dealing with some complicated proofs. Here instead, let's conclude this section with some non-commutative examples. Here, 2 by 2 matrices with entries from Zm is a non-commutative finite ring with unity. Zm is a commutative ring with unity, and you can put matrices with these, with 2 by 2. And of course, you can consider square matrices of larger order too if you want to. But if you want just an example of a non-commutative example, 2 by 2 is just as good as any. The inverse, okay, this is the identity matrix. This is a unity, and that's the inverse. But this AD minus BC down here in the denominator can be 0 in some cases. So this is not a field in general. And subring by keeping the second row as 0. Okay, all right, let's keep that open. But second row as 0, then you're going to get a commutative finite ring, but this time no unity, because you see, unity is this one here. You're not going to get unity from here. Okay, those are some non-commutative examples, but I'm not going to do too many about non-commutative examples, so let me de-emphasize that in gray back again. And as for Fermat's theorem and their applications, well, we're going to discuss those in next several videos.